Hello, this is our machine design project number 3 presentation. I'm Brandon Porth.
I'm Michael Bykowski.
Rema Johannes.
I'm Max Porter.
I'm Christian Tello.
So starting off with our problem statement, we were tasked with designing a gearbox for a small gasoline engine powered air compressor that fits under the infinite life criterion provided. For our deliverables, we designed the shafts, chose the gears, the bearings, and the couplings. First, we designed 2 individual shafts with a factor of safety of 2 and infinite life, then chose appropriate gears, bearings, and couplings that were spec'd for the critical locations and rated loads.
So the air compressor will operate with a 10-year life of 1 shift per day, 5 days per week. And in this instance, the client's required gear ratio is a 2.5 to 1 reduction in velocity from the input to the output shaft, and the input shaft's velocity is 750 RPM. In this specific application, the torque time function on the output shaft isn't uniform, and special consideration will need to be given to the torque at various crank angles. For the sake of developing a comprehensive calculation package, there were certain assumptions that needed to be made and certain minimum design requirements. By and large, this means that the minimal factor of safety for any system is 2 commercial grade spur gears will be used with teeth that mesh in full depths. Any stock materials may be used, and the expected system reliability is 95% with bearings. All gears will be spec'd from Boston Gears, and all bearings will be shielded and spec'd from SKF.
Design and material assumptions were made for the sake of developing a comprehensive calculation package that meets customer specifications. Per the customer, all systems must meet minimum safety factors of 2 and maintain 95% reliability. To minimize cost, commercial-grade spur gears will be used with teeth that mesh in full depth, and shafts will be of standard sizes and materials, and there will be no torque lost in transfer through the gear mesh. As mentioned earlier, the desired gear mesh will have a 20-degree pressure angle and a diametral pitch of 6 to allow for a larger selection for torque applications. Using MathCAD, gear and pinion tooth numbers were justified by finding the minimum number of teeth acceptable using design parameters and assumptions. The mesh was verified by calculating an appropriate gear teeth contact ratio. Generally, a contact ratio of at least 1.4 is sufficient, and ours was 1.7. In addition to large radial forces at gear and bearing locations, stress concentrations from shaft keyways and shoulders were inspected for failure likelihood. Assigning standard materials to our shafts, we took a conservative approach selecting size factors, surface factors, endurance strengths, and material strengths using the D.E. Goodman equation. A minimum shaft diameter with a safety factor of 2 was calculated, sized up to the next standard imperial dimension, and used to recalculate safety factors in the shaft. Knowing the critical locations for yielding and a keyway, we then calculated material yielding safety factors and the required keyway length to resist crushing and shear failure. Shaft number 2 followed a similar iterative approach to calculate minimum diameters, critical dimension safety factors, and ultimately the likelihood of failure. Because shaft number 2 experiences higher torques, we also chose a higher strength steel in order to keep the shaft diameter economical and maintain a safety factor greater than 2. After shaft design verification, bearings were selected. Knowing desired life and reaction forces at the bearings, we calculated our desired load rating, enabling us to select suitable deep groove ball bearings. The final task was selecting an appropriate coupling solution for the output shafts. Using the calculated torque at the output, a coupling of appropriate shaft diameters and torque rating was selected from McMaster-Carr to be able to adequately handle the sustained load.
There are numerous components and dimensions to report on. Firstly, the gear mesh was selected from Boston Gear using a 24-tooth pinion and a 60-tooth gear. Both gears are above the minimum tooth count of 15 calculated. Next, the shaft analysis was performed using a conservative D.E. Goodman approach as mentioned before. Shaft 1 is a step with a minor diameter of 0.625 inches and a major diameter of 0.75 inches, machined from 1020 cold-drawn steel. Shaft 2 is also stepped with diameters of 0.8125 inches and 1 inch, machined from 1050 cold-drawn steel. Both shafts are machined to standard dimensions and use standard steel, minimizing the fabrication costs. Furthermore, the factors of safety on both shafts sit above the minimum 2.0 specification. Some of these characteristic dimensions just listed are in the photo provided. For the selected bearings on shaft number 1, we calculated a load rating of 631 pound force based on desired life and shaft speed. For shaft 2, the bearing load rating was calculated at 465 pound force for the slower shaft speed and resultant forces. Both bearings selected meet this requirement. Here's a quick summary of all the components used in a table.
In conclusion, the resulting gearbox design and calculations make logical sense given our current level of engineering intuition. All of our factors of safety are above the 2 minimum. However, the 2 minimum may not be large enough as we have not done any physical validation or FEA. The next step in this process would be doing more FEA and physical validation or increasing our factor of safety. This design benefits from being a robust single mesh without multiple gear trains. The system is designed to fail at the keyway first to save on more expensive components. And our gearbox benefits from no axial load that would result from angle cut gears. The gearbox is, however, relatively heavy and large for the amount of power it's transmitting. Further iterations may be done to reduce the overall size of the gearbox.
And this concludes our machine design project number 3 presentation. Here are our references.